interested in delivering of the fundamental understanding of electricity that I couldn't resist. So I just kept adding slides and kept adding slides and kept adding slides, and it grew and grew and grew. So I hope you enjoy it.
Taking blue. Excuse me.
So Hannah, Ava, how you doing?
Good, good.
Excellent. Great to hear it.
You are. Just look at me. Maybe I could. Victor. No.
He just wants to participate, that's all.
Okay, I guess I should have announced that we have the same Zoom link every time. Because that seems to be the confusion. Okay, let's see.
Same bat time, same bat channel.
That's right. Let's see. Yeah.
There's a robotics competition in Houston right now.
Really?
I think it's the World Championship.
The World
Kids
Championships
from
in
like
Houston.
Brazil.
Mm.
I posted a link on the Modern Educators page.
That's pretty cool. It's always interesting to go and watch those things, because if I understand correctly, they kind of frame what the challenge is going to be for them ahead of time, and then just let them go crazy trying to create a robot that'll do it, better or faster or
Yeah.
or what have you. It's
One of the girls from their scouts troop is in the competition.
nice. Yeah, that's the cool thing about technology like that, is it's progressed so much that on a consumer level, it's become affordable for anyone to pick up a kit, if you're interested and learn a lot about the fundamentals of electricity and logic and coding and
Yeah.
battery life and sensors and feedback, and it's pretty wild.
It's awesome.
See how far it's come. Yeah. All right. We'll give it one more minute. Sorry, you're so far away. There you are.
I'm Sawyer.
Hello, Sawyer. You're Finn. Okay. Nice to meet you, sir. You looked tiny when you were way back there and there's Oliver.
Hi.
Man, nice to have you.
Thanks.
Do you guys feel energized to talk about electricity today?
Yes, I like electricity.
Yeah.
Me too. All of us should, even if we don't.
Yeah.
Was everybody able to get through the lessons okay?
Yeah.
Emma's not in. Just a second.
Yep.
Good deal. I was reviewing some of the grades and stuff today, and I think there was, I understand that the lessons, like the material that you review before you take the quizzes, may not always give you the direct answer to the questions on the quiz, but they require you to kind of deduce or think critically and infer things a little bit. So if you have any questions, we can answer those up front. If there was something that you just didn't understand, even after re-reviewing the material, happy to answer those questions. The other thing we're going to do today is start with a bit of a review of a concept that I think is important to understand, and was based on the material in the last lesson. And that was power consumption and how to calculate kilowatt hours, kind of what a kilowatt hour is. Hey, Em.
She'll be right back.
Hello.
Okay,
There she is.
all right, perfect.
No. Mhm.
Okay, well, we got more than half of the students, so
Yeah, we usually
Think-
about 16.
I think we should go ahead and get started. Like I said, we've got a full hour plus. We went over last time, so I fully anticipate this to go beyond an hour this time as well.
Yeah.
Welcome everyone to lesson 2 of our Introduction to Energy class. Again, I'm your host, Mr. Mike. Today, I actually wanted to start with a review of a concept that we saw last time. We talked about different examples for how to calculate the cost required to use energy. And in this case, we're talking about the cost of electricity. I think the example they gave was comparing a hair dryer and 5 light bulbs and which one would use more energy. We took that a step further and said, well, if energy cost a certain amount per unit, kilowatt hour, how much would it cost to pop a bag of popcorn, for 3 or 3.5 minutes, something like that. So I got the feedback that a kilowatt hour still wasn't really making sense. But because it is literally the unit we measure electrical consumption in, I wanted to review it and make sure we had a chance to look through it step by step. So I came up with my own problem, and this one is baking a potato in the microwave. Anybody ever done this?
Yes.
No.
Definitely.
No?
I don't think I ever have.
No.
I don't like potatoes.
I thought
I
they
heard-
baked potatoes in an oven.
No, it's in a microwave. If you want it to be quicker.
You can. You can bake you can bake a potato in a campfire if you want.
Yeah,
But
we've done
We've
that. I
tried
think we've
that.
done that.
Yeah.
Microwaving is a pretty quick way to do it, and it's hands off, right? You just don't wrap
Yeah.
it in foil.
Air
Air
fryers
fryer.
too.
Yeah, exactly. So if we know how much, this is kind of a word problem. If we know how much electricity costs per kilowatt hour, about 15 cents, how much would it cost to bake a potato? If we're gonna take 10 minutes in a 1200 watt microwave. So anybody want to lead us off onto the solution here?
For the watts, it would be 1.2, correct?
That's that you're converting kilowatt
Yes.
or watts
Yes, to
to
convert it.
kilowatts. That's right.
Would that be?
That's a good first start. Sure. Because we're trying to get to kilowatt hours, right?
Mhm.
So if you're given the power consumption of the microwave in watts, you just converted it to kilowatts by dividing by 1,000, right? Because there's the prefix kilo means 1,000. So if there's 1,200 watts, that is equal to 1.2 kilowatts, right? What else do we need to do?
One spring roll each and some.
All right. So converting the minutes to hours.
That's right. Because it's kilowatt like I said up here, recall that a kilowatt hour, or kWh for abbreviation, is 1 kilowatt times 1 hour. So to find out the cost, we need everything in kilowatts and hours, but we were given watts and minutes. So we need to convert minutes to hours as well, right? And it turns out, depending on how far along you are in your studies, if you haven't done fractions or unit conversions or any of that yet, don't let this bother you. You'll learn it pretty soon. But in general, comment, question. In general, when you convert minutes to hours, 10 minutes ends up at about 0.17. And just to help illustrate this a bit, what happens here is your minutes cancel out here. And when you multiply this conversion through, you just divide 10 by 60, which is the number of minutes you have divided by the number of minutes in 1 hour. And you convert minutes to hours and you end up with about 0.17. Okay, pretty easy, right? Okay. So we already talked about converting the microwave's power rating from watts to kilowatts, right? We're trying to get to kilowatt hours. So we do the same thing here. There's a conversion factor. 1 kilowatt is 1,000 watts. So when we do that conversion, we end up with 1.2 kilowatts. Same way, right? Watts cancels out here, and we're left with kilowatts, and we might multiply through. Okay, so then what do?
You multiply it.
That's right.
The
You
kilowatts.
multiply 1.2 kilowatts times the number of hours or the time you're going to use those 1.2 kilowatts, and you get
I don't want sweet and sour.
about 2 kilowatt hours.
About 3 cents.
Right? That's right. About 3 pennies is how much it costs to microwave a potato for 10 minutes.
That's not a whole lot.
It's not, is it?
But if you eat a lot of potatoes,
And who microwaves 1 potato at a time?
I know.
We're in
I was
Idaho, the
microwaving
home of the
lunch.
potato.
Right? Yeah, so you can calculate the concept here is that you can calculate the energy cost that required to do almost anything, use any appliance, right? Because all appliances have a power consumption rating in watts or kilowatts, typically in watts. And you can figure out, you're paying for electricity, so you can figure out an average cost of that electricity, and then figure out how much it costs you to do certain things. It may lead you down the road of potentially thinking more about how much you're paying for the power you use, and maybe thinking about using less or finding other ways to do things that don't cost as much. So is everybody okay with this math and the concept of kilowatts and kilowatt hours?
Yeah,
Awesome.
I think, yeah.
Yep.
Awesome. All right, so on to today's lesson. I hope this picture doesn't summarize your first introduction to electricity. I can honestly say I have been electrocuted before. I don't know whether I looked like this at the time that I had, but certainly
guy from Home Alone.
it is. Good call.
Oh, it is.
Oh, I haven't
So,
seen Home Alone in
Were
forever.
you like struck by lightning or just struck by a socket you were working on or something?
I've been shocked so many times I can't remember.
Does your hair go up or is that just like
And you
weird?
survived every
No,
one.
That's right. There's some Hollywood magic involved in this one. You don't actually turn into a skeleton, as it turns out, because here I am, No, this, I kind of wanted to lead this because it's funny, but there's a couple of lessons in there. Like, why do we want to talk about electricity? I think as we saw last time, we use electricity every day for a lot of things, right? It's an essential part of our daily lives, but it's also a dangerous one. When I can't start talking about electricity without kind of describing some of the risks. And Home Alone, the movie, made fun of this guy getting electrocuted, which is silly in nature. But what I don't want you guys to do is take away from this lesson a sense that electricity is so essential that it must be safe, right? It's everywhere, it's all around us, so there's no risk to it at all, right? I have to state quite the opposite, that electricity is not to be played with. It does provide essential things in life, including energy.
It sounds like fire.
It can create fires, yes. Most, well, I won't say most, but a lot of home fires or fires that start in the home are caused by issues with electrical circuits. And that's why I say it's not a toy, right? Obviously you should not play with electricity or electrical devices, right? They're made to work a certain way. And if you ever have any questions, stop and ask a parent, right? It's best to be conservative when it comes to using and being around electricity. Who knows, or who can guess when electricity was discovered? How old is it?
1800
years ago.
Franklin.
It was like the 1700s was the first time that it was.
800s, 1800s.
That's AD, right? I hear
What about-
1800s, 1700s. Those
Yeah,
are all common
somewhere.
conventions.
The thing is, like, there was lightning, like before there was
Yeah.
like we had like the actual,
That's right.
like before we
Does it
knew how to
count?
like harness the electricity, we could still see it in
Very good.
different ways.
The physics of electricity have been around forever, right? For as long as the universe has been around, electricity has been present, right? The physics that cause electrons to flow, and we'll see a little bit more about that in a second. But the first known study of electricity was actually in 600 BC. So that's how many years ago is that? It's 2023, so it was 2,600 years ago.
Oh, that was the Greek guy. He was rubbing a piece of amber on animal fur.
That's right.
Yeah.
That's right. And what he observed and told others about were the little electric sparks you get. Have you ever worn socks on a carpet floor and then touched a doorknob?
No, I've
Nobody-
never got shocked
Yes.
by doorknob.
Yes.
But on a
Oh, man.
trampoline, you usually get a lot of static.
No.
That's right. That static electricity is what that ancient Greek observer saw. And he documented, he's like, wow, man, there's these little bitty lightning bolts that I can see when I do this certain thing. So he's actually in some circles credited with discovering electricity. Even though it was static electricity, it's the same thing. It's flowing electrons from one place to another.
Never been a fan of static electricity.
Yeah, I was always very uncomfortable.
Anybody who's been on a trampoline with others or worn socks and slid across a carpet floor has discovered static electricity at one time or another.
Or folding
Interest-
a lot of clothes.
Yeah, that too. That too. So someone said 1700s. I'm assuming you were referring to Benjamin Franklin and the famous kite, string, and key
Actually, no.
experiment. No? What were you referring to, Lola?
There was one time, I think it was in the 700s before Benjamin Franklin or whatever it was, Thomas Edison, who made a battery that could conduct electricity, but they had no idea how it worked.
The kite and the key.
Not
No,
familiar-
it wasn't the kite and the key.
not familiar with that story. I'll have to look that one up myself. Benjamin
It was in
Franklin's
one of the videos. It was in one of the videos that you put on there.
okay. Yeah, I'll have to go back and review that. I asked because Benjamin Franklin's experiment and his writings about grounding lightning to the earth, and it's attractive, between the attraction between positive and negative forces was in the 1700s. It turns out that we didn't actually modernize electricity and generating it as we use it today until 1831, when a guy named Michael Faraday, a British scientist, figured out how an electrical generator can actually work. So there's a huge time gap from 1600 BC when people begin observing and documenting static electricity to modern electricity generation in 1800s, right? Even if Benjamin Franklin and some others were playing with their lives, dealing with lightning. All right, so another quick review, right? We're going to talk this lesson about electricity, but where does our electricity come from? Last time we looked at a breakdown
don't-
of, well, for Newfoundland and Labrador, most of the electricity that is used in the province comes from hydroelectric plants of 96%, which is still a staggering number to me, but it's true. You look it up and there are, and we'll look at how that works. There are a number of hydroelectric facilities across the province as well as across Canada that generate electricity for the country. In Texas, it is predominantly fossil fuels. If you look at coal and natural gas, they make up over 50% of the power generated. Solar is a very small percentage, and wind is actually almost a quarter. So how does electricity work? What is electricity? Can someone describe to me what electricity is? How it works?
Electricity is like
The electrons move
Flow of
from atom
electrons.
to atom very quickly.
Very good.
flowing
Yeah,
pattern.
the flow of electrons from atom to atom whenever they
Causing-
get excited, jumping to a new orbit.
Perfect.
causing the electrons to move in an orderly fashion, like orderly line from one place to another.
It is somewhat orderly. I will give you that in the way that electrons have to be in their outer valence shell. If anyone has taken Miss Tara's chemistry class, you'd have covered this. But for an electron to leave a particular atom, it has to have enough energy. It needs a push, an excitation, a you're no longer welcome here, move kind of force that makes it jump from one to another that has availability, right? It's got to go from one to, it can't just go from one to nothing, right? It has to go from one atom to another. It turns out that the most common conductor we use today is copper. It's predominantly copper atoms in solid form drawn into a wire. But if you zoom in on the atomic level, you would still see this mechanism at play. I noticed on the quiz there was some confusion about the subatomic particles that exist at the center and carry a specific charge, but the construction or the anatomy of an atom stays constant. The nucleus, not a subatomic particle, but a combination of protons and neutrons, is at the center of the atom, and the electrons orbit kind of like planets around the sun, in different layers or different distances from the nucleus around it. So those electrons are kind of whirling around in clouds and layers around the nucleus with electromagnetic forces, positive, negative, negative, positive, holding them together as an atom, right? And that's strong. Go for it.
I said in that question, I said that the nucleus was the center of the thing, and it said I got it wrong, and I was confused.
The nucleus is the center, but the question asked specifically what the subatomic particle was, which is a proton.
Oh yeah, and Mr.
What
Mike.
was that?
Does that make sense?
Yeah.
Yes.
Okay. You weren't the only one, trust me.
Well, Mr. Mike.
Yes, sir.
What about like because whenever I put in nuclear force for what holds it together, it said it was electromagnetic force, and
right.
and the strong nuclear force holds the nucleus together. So I had been confused on that one.
Yeah, that's it's pretty easy to see how that would be confusing, right?
Yeah,
Yeah.
just after our nuclear chemistry class, the four forces.
Yeah.
Do you remember how much stronger the electromagnetic force is than like gravity?
Like
Yeah,
a million.
Electromagnetic is like what 43 to the 10, no, it's like 10 to the something.
10 to the 16th, I think.
Yeah,
Pretty
yeah,
strong.
it's much stronger than gravity.
If I remember correctly, gravity was the weakest on that chart.
That's right.
Mhm.
Yeah, and then what Levi said, then you have the strong force and the weak force that's inside of the nucleus. Yeah.
The weak force ain't so weak.
That's right. And it's also good to know, especially with this slide here, that we learned in chemistry class that electrons go to protons, right? They go to the opposite charge.
Mm-hmm.
Okay. because current's gonna do a little something different.
Opposite charges attract, right? That's the idea.
Yeah.
The other thing to consider is that if you decide to pursue a career in engineering, you'll learn in thermodynamics that things move from areas of greater concentration or density to lower, just like Bernoulli's principle, where things float. Whoever's drawing on the screen, please do not do that. Things of less density tend to segregate vertically, vertically in space, versus things that are greater in density, right? It's hot air works the same way. Hot air is less dense, so it rises. Colder air is more dense, so it falls to the lowest level it can. Okay, so we've seen the anatomy of an atom. Now, how does electricity work? If you take 3 atoms and you put them next to each other, let's say in a copper wire, copper's a solid, the atoms aren't really moving relative to each other. It's a solid, so they're kind of fixed in position. They have a certain number of electrons in their outer shell. They have protons and neutrons at the nucleus, and they're all held together. If you take, and this is kind of the concept of electricity generation, if you induce a negative force or a charge on one side, if you say cause those electrons to want to move between atoms, it takes a push. Sometimes they call it a pushing force, but if you induce a negative charge onto one side, what you can actually do is kind of like in bowling or in a pendulum, one electron will jump from one atom to the next, which will cause another electron to jump to the next and the next and the next and the next. And depending on how consistently and constantly you apply that negative charge, you can get these electrons to flow across all the atoms in the copper conductor and create electric current, right? So if we look at the top of the page, we see a very zoomed in atomic level view of this happening, where on the left you have this incoming negative charge or this electron push, and then 2 of these electrons jump to the next one and then to the next one. On the next level of the drawing, you zoom out a bit further so you can see 6, let's call them copper atoms, and it's happening across all of them. And then you continue to zoom out, and you can see where the picture starts to resemble what might be considered a copper wire. You know, if you kept zooming out, this thing would look solid at some point, and you would have electric current flowing through it, because on one end, you're inducing this electron, this negative charge, this push, and it causes electrons to flow along the length to the other end.
Yep.
Does that make sense?
Yes.
Yeah, somewhere on the
That's
other
it, right?
side, yeah, like you'll have a metal on one side, like zinc's a good example, and its valence electrons are gonna have an affinity or a pull towards copper, because it's gonna be wanting their electrons, right? There's some sort of positive force that's going negative to positive, and it's gonna flow through a wire.
Okay, so the second part of the lecture was on the science and sources of electricity. So can anybody tell me the 2 main ways we make electricity globally?
Water.
Try again.
Generators.
Heat.
Generators and
Solar.
Turbines.
Turbines.
solar.
Solar.
Solar. A turbine is a type of generator, or is coupled to an electric generator. And we'll see that in just a little bit. Water was close, but water is something we'll use to actually turn the turbine itself. That makes the generator turn, that generates the electricity. So the highest level answer we were looking for there, the concepts you should take away, is that solar, which is different than a generator, it's a different mechanism altogether, and generators, which are really just copper wires turning in a magnetic field that creates a current. kind of like we just saw. It turns out that most of the world's electricity is generated by generators. Solar is becoming more prevalent, and it does have some benefits, but it also has some drawbacks. So if you look at how a solar panel or a group of photovoltaic cells works, it uses sunlight, right? It doesn't use steam or kinetic energy or anything mechanically related other than chemistry to make electricity. Photons from the sun, starting on the left, photons from the sun hit a multi-layer semiconductor material that also has copper conductors run through it. So the electrons have a preferential place to go. You know, they'll line up and find this copper and then flow down it. The photons hit this, what is typically silicon, sandwiched together in layers, and those photons actually provide that excitation force to the electrons in the silicon, which induces electron flow. So photons that are, you know, almost invisible, right? They're visible light, but it's the energy from associated with the sunlight that'll come in and actually strike the silicon atoms and create the electron flow. The other piece of the solar panel is really the path, the copper that provides a path for the electrons to flow, kind of these gold bars you can see up here, gold colored bars. And then the return channel for the electrons to come back, right? So you'll get a flow of electrons through the conductor, and they'll be connected to a load, or in this case, this light bulb. The electrons will go into the light bulb through the filament, which gives off light, right? It turns the electron energy into light. Most of that energy is wasted as heat, as it turns out. And then the return path of the current takes it back to the other side of the solar panel, where the process can start again. So if solar panels are just use sunlight, what could be some of the drawbacks?
Nighttime. Clouds.
It's a big one.
Too hot.
Heat can affect the crystalline structure of the silicon, which is necessary for electrons to flow, right?
Bad weather and other types of things that may darken the sky.
That's right. What happens if you don't have sunlight, which tends to happen for 10 to 12 hours a day? You know,
No electricity.
no electricity.
No power.
None at all, right? So that's one of the major drawbacks, but one of the major benefits of solar is that silicon, the very thing we use to create them, is one of the most abundant minerals on Earth. It's readily found in the Earth's crust, and it makes up a large percentage of the chemical makeup of the Earth's crust. So it's easy to come by. You still have to spend energy to manufacture the cells and, you know, make the copper conductors and the glass covering that goes over it to protect them. But the other big benefit for solar is that as it generates electricity, you don't have to burn any fossil fuels to do it. So they are considered close to zero emission sources of electricity, right? So later when we talk about, you know, emissions and preferences of some energy sources versus others, when you talk about electricity specifically, solar panels are prevalent because they do have a large upside in that they don't produce any emissions. It still takes some to manufacture them, but it is one large upside. A couple of other cool facts I learned when researching the topic was that every hour of the day, the sun produces and imparts enough energy in the form of sunlight onto the earth to power the world for a year.
Hmm.
How does that
Impressive.
How does that hit? Yeah, feels like a lot of energy, right? I thought so.
It is. For the solar panels, could we like make a store some of the energy for later whenever it's night or cloudy or?
Absolutely. In fact, most solar installations will come packaged with a type of battery that can store some of that energy. Battery technology is still evolving, but to power your home at night, depending on your energy demand, you have to have more or less batteries. Batteries have a finite life, just like solar panels do. They tend to only last between 10 to 30 years, depending on whether you're talking about the batteries or the solar panels themselves. They lose efficiency over time, and you actually end up wasting more energy. The other interesting fact about solar panels is that because of the way they're made, their crystalline structure made from silicon, they can only actually convert a theoretical maximum, meaning like all other anomalies aside, if you calculate the amount of electricity you can get out of a solar panel, it's only about 40% of the sun's energy that's hitting it.
So we can't
So-
really harness all the sun's energy.
Not all of it, no.
We have
Not
to
with
make
current
something
solar
different for that.
But you'll have to have improvements in solar, in photovoltaic cell construction. I say construction loosely because I don't have a better word for it right now, but just the way we understand the technology to work and the way we make them today, it can only be about
Mhm.
40% efficient. So that just means to get the same energy out of it, you need more of them, right? Just like the battery concept. If you need, 100 kilowatts to power your home at night, and a battery or a solar panel can't give you that, you need 100 kilowatts from a battery. If a battery can only hold 7.5 kilowatts, you need at least 2 batteries, right? Well,
Mhm.
you need at least 20 batteries, excuse me. And batteries take up space and they're heavy, and they most of the time contain elements that are not meant
Not
for human
healthy
interaction.
for you.
That's right. That's right. Even latest technology like lithium ion, lithium is in large doses toxic to humans. And lead acid batteries even worse and heavy. So it's not all golden with solar panels, but it is promising, right? Risks can be managed, efficiencies can be accommodated. One of the other cool facts I found when researching solar is that, especially for our Canadian folks, in 2010, Canada had the world's largest solar power plant. It's called the Sarnia Photovoltaic Power Plant, and it's just west of Toronto, and has the capability of generating 97 megawatts. That's millions of watts of energy.
Great Wi-Fi there, I guess.
What? Yeah, you could say that. I bet they've got it on Wi-Fi now. So any other questions on solar before we move on?
Mhm.
How
This doesn't
sunny
have-
does it particularly have to be for the solar panels to work? Does it have to be like a clear sunny day, or can there be a few clouds blocking the sun?
That goes into the efficiency equation, where direct sunlight provides the most energy to the panel, and it will produce more electricity. If it's overcast or partly cloudy, there's not as much energy from the sun getting to the solar panel, so it will produce less. If it's daylight outside, it will produce energy because there's still photons coming through, right? But it won't produce as much. So if you do a study, and you can do this actually in Google, I would encourage you to do it. If you go to Google and you go to Google solar, if you put in an address, it will tell you how much solar energy you can generate from a given size of solar panel array, which is pretty cool. You can use it when
That
you're
is-
thinking about installing solar panels on your house.
I'm gonna use that to see how much solar power we use.
Google
I-
solar.
I wouldn't use,
Probably don't use much.
yeah.
I
Well, if you don't have panels, you're not using any.
Code.
I was wondering, you said you were talking about pendulums, and I thought, well, why couldn't you use a pendulum in some way to generate electricity? Would there be a way you could do that?
Sure, but a pendulum works on converting potential energy to kinetic energy. If you take the object and you raise it up and you let it go, or you raise it up and you give it potential energy, when you let it go, that potential energy converts to kinetic energy as it swings through its path, which could be used to turn a shaft on a generator. But how do you keep the pendulum going is the question.
Well, I thought you might be able to like do something that would make it have like almost like extra energy like left over every time it like hits itself back and forth.
Ooh, you could do,
Almost.
that's a good idea. You could do a magnet on either end or something.
Unfortunately, what you'll find in physics is that the energy conversion from potential to kinetic, some of that energy gets used to turn the generator and make the electricity. So every time that pendulum goes through its path, it's losing some more of that kinetic energy, and more and more and more, and then settles at the bottom. You would have to have a way to put more energy into the system to continue to turn the generator. But I like your idea.
So then you just kind of get to the first problem again. Where do you get the energy?
That's right.
But where
Takes energy to make energy.
Mm.
Speaking of which, this one's a little bit more theoretical because it's difficult in everyday life to see a generator, an electrical generator in action, right? Some of you may have backup generators at your house or portable generators. I think, Ms. Tara, we at the house have an emergency broadcast radio that works on both solar, has a small solar panel on top, and on the back has a hand crank. Yeah, Emma's holding it up there. Can you show them the solar panel on top? So that portable radio has a rechargeable battery in it, Desi, like you were talking about, where the sun will actually hit that little solar panel and it will charge the battery inside of it. So that when you, in an emergency, if the power's out and you need to listen to what's going on, you can power that little radio and receive information based on the energy that battery holds. In the case the solar panel doesn't work or it's nighttime, it has a hand crank on the back, which takes the place of that pendulum, and all you do is sit there and turn it, and it creates electricity to charge the battery, and then you can listen to the radio.
Mhm.
They're pretty handy in a pinch.
How long do you have to spin it?
Not long. Not long. It depends on how much, how drawn down the battery is. If the battery doesn't have much charge left in it, you may have to turn it for 10 minutes, 15 minutes to get it to charge back up. And then you can listen to the radio until the battery is out of charge, right? Or has no more electricity stored in it. So that concept of turning the crank and generating electricity is a small scale example of how an electric generator works, right? And you can think about this in two parts, or it helps me to do that, where the electrical generator is what we see in the top right-hand corner of the screen, where in some combination, there are magnets with a north pole and a south pole, right? So you get a difference of charge across them, and a copper wire that's coiled around. And as you spin that copper wire, that copper coil in between those magnets, it creates that electron push, right? Because you got negative on one side and positive on the other. And as that copper goes around, it sees the negative push on the other side, and all the electrons in the copper wire say, hey, move. I don't want to be close to you. I don't like other negative charges. I'm going to run away from you. Right? And then you spin it the other way and it sees the positive charges, so they all race to the other side, right? And because one end is connected to the positive side and one end is connected to the negative side, it creates a flow of current through the copper wire. That's how all electric generators work. It's just that simple. They can be larger or smaller depending on the amount of electricity they generate. But that's how they work. The
How
next
fast
part,
do you have to turn the crank?
it depends on how much electricity you want to generate. It turns out there's an optimum speed based on the phase and voltage that we use in North America. And it's about 3,600 RPMs. There's some math behind that, but we use 120 volt, 60 hertz energy for most things. It may be transmissed at 240 volts or higher, but the 60 hertz is the important part, because 360 RPMs is a multiple of 60. So it's easy to get the phase electricity we want out of it. Does that make sense?
Yep.
Sort of.
There's some higher level physics involved there, but that's the basics.
What are the blades?
Yes, so that's the second part. Number one is the electrical generator. This is how we make electrons flow by turning this coiled wire or magnets inside of the other, and electrons flow. But how do we turn that shaft? Like, if I can annotate real quick, how do we turn this up here? You can see it says connected to turbine and it shows it turning.
Air, wind, I think.
Very, very good. Wind is one way you could do that. That's actually how a wind turbine works. So we
I
talked.
learned that from a Storybots episode.
You can learn something from anything, right?
Yeah.
But to answer your question, Desi, the blades are the things that are in the turbine. If you look at your ceiling fan, it has blades too. And all they do is use electricity to turn the blades and produce air movement, right? To keep you cool, or to move air from the top of the room to the bottom. Now, if you reverse that process, if you blew air across those blades in the ceiling fan and the electrical motor in the ceiling fan was set up correctly, you could generate electricity with it. It turns out that most of the world's energy that comes from generators uses this concept, but instead of using the motion of air, it uses steam. We will take a fuel source, whether it's nuclear or coal or natural gas or oil, and we will burn it, which will heat water. That water will turn into steam. The steam will travel, as you can see in the picture down here, the steam will travel through turbine blades that are designed to get the maximum energy out of that steam and into this shaft connected to the generator, which will turn the electric generator, right? You're just using high pressure steam to come through there and turn the turbine, which, like in the top right picture, turns the shaft that the coiled wire is connected to. And the generator makes electricity. Emma did the same thing with the hand crank on that radio. She was acting as the turbine, right? On a larger scale, we use combustible or burnable fuel sources to heat water, produce steam. We use the energy in that steam to turn the blades of a turbine, which turn the shaft of an electrical generator. You can do this in a lot of other ways. We talked about wind, but for the Newfoundland crowd, most of your energy comes from hydroelectric. That works just like this picture in the bottom. you have a lake on the left-hand side with a tall column of water that is at a very controlled rate allowed to flow across the blades of a turbine down into a lower reservoir or river. And that turbine, the flow of that water across those turbine blades, turn the shaft of an electrical generator, which produces electricity. Right? So that's just using flowing water. Anybody seeing a parallel with solar?
Mm, I
How
think
many, how much emission, how much combustion emission do you think a hydroelectric plant produces? Is
A
it
lot.
burning? Is it burning anything to turn
No,
No.
the turbine?
no.
Nothing. Very
No.
low emissions. Very low, if zero emissions from a hydropower plant. That's why where you have the ability, we talked about the Hoover Dam before in the United States. If you have the ability to build a dam and meter or control the flow of water from the high side of the dam to the low side of the dam, you can use that energy to make electricity. Pretty neat, huh?
But then the blade would eventually rust, or do we not use metal?
They can. It depends. These are highly engineered devices. I'll put it to you like that. I'm
Highly
sure they've
engineered
thought of
devices.
the water chemistry, and the blades of the turbine have been tested for compatibility, and they've made sure that this thing is going to last some number of years so that they know they're going to get so much electricity out of it, and they'll get their value back from producing that electricity, because they will sell that electricity to consumers.
I hope they filter out the fish.
Yeah. Fish electricity.
Do they just turn up fish in there? I mean, like,
So
Fish
I'm
comes out
not-
of your power socket.
I'm not advocating for it, but you brought animals into the equation. So has anybody ever had a hamster as a pet?
No.
No.
Have you ever seen a video of a hamster in its wheel, in its cage?
Yes.
Yeah, I've
Yes,
seen-
I've
yeah, I've seen
seen
those
many
before.
videos of like a hamster wheel powering something.
Do you think you could use a hamster to create electricity?
Yes.
Yes.
Yeah.
Well, not a lot, but
but you'd be able to
If
create
you got
Charge
something-
your phone or something.
possibly.
it'd
What
be
if-
inconsistent because it would want to take breaks.
You could
That's
create
why we
hamster
use
powered
Feeding it
machines.
cars.
carrots.
Just like the hand crank on that radio. You get tired eventually, right? But what if you still needed electricity? Why not create a machine or a fuel source that you can burn without having to put any human intervention into it, other than monitoring and making sure the fuel is there to burn and the steam is coming out at the right temperature, pressure, and the turbine's working, you know?
Mhm.
Why not do that instead, right? So everybody's got the concept of generators, because like today, this is what we use for the majority of the world's power needs.
Yes.
Awesome. I challenge you to find examples of generators around your home, because I guarantee you there are at least one or two.
Right in my hand.
Em's got one.
Like
There's
find
at
them right now.
least one I can guarantee you.
We
of.
have a literal generator outside that we call a generator, so that's
We have a we have like the, you know, that little can opener, and you can move your hand and it'll open the can or something. Does that count?
It doesn't.
All right.
That's
That's
not
handheld.
generating electricity.
Oh, we
That-
have one that does it by itself though.
Does it have to be plugged into the wall to work?
No, it has batteries in it.
Okay, well, that's using electric current from the batteries to move the can opener. That's not a generator, that's a consumer.
It's creating electricity out of gasoline.
I got one.
That's what portable generators do.
Oh,
That's
the
right.
car? The car.
Exactly. The alternator in your car is a generator. There's
Television.
actually some pretty cool projects you can do with those too. I've seen, you talked about college robotics competitions. I've seen colleges have contests for which team representing which college can generate the most electricity from a bicycle. Something that you get on and pedal and turn a shaft hooked up to car alternators to generate electricity. You become the fuel source, right?
Mhm. Oh, I've seen those before, like where you pedal on a bike, create some
Yeah,
electricity.
turn on a light bulb.
That's right. That's right. So if we don't have a large generator outside of each of our homes supplying power directly to us, how does it get to us? Where does it come from?
The energy people.
Power plants.
The energy people. We are the energy people.
I'm sorry. The like power plants that make the energy.
That's right. It turns out that it is more efficient for large power plants to create enough electricity that can be distributed to rural areas, to cities, to small towns, anybody that needs it, right? They can take a small piece of land, put an electrical generation plant on it, and supply the needs for the surrounding area, depending on its demands, right? We tend to not be aware of where these are unless they're very large or they're nuclear powered.
Because there won't be like next to big cities or anything.
They won't, right? They'll be some distance away because if they're burning fossil fuels, they tend to be loud. If they're, and they tend to have or give off the most emissions, right? So you don't want to live next to that. You don't want to inhale the burnt remnants of fossil fuels, right? Which they do a lot to clean the air, but they still give off emissions. So it's not desirable to have those right outside your door. We take advantage of something called the electric power infrastructure or the grid, right? And what the grid is, as they explain in the videos, it's the way power gets from the plant to you. And it does a lot of things in between, right? I guess there's a number of electricity generating things on this page, but if you kind of look toward the top left, you see the distribution station. You could, if this wasn't a solar power grid, you could replace the solar power grid with a coal-fired or a nuclear or a natural gas burning power plant that generates the electricity. And like the video said, the electricity comes out and it gets stepped up to a super high voltage to be transmitted through overhead power lines to a distribution station. And what the distribution station does is then branches off the electricity to go to different regions, right? So there'll be a distribution station pretty close within reason to the power plant, right? Because the sooner you get it to a distribution station, the more energy gets there and the more places you can send it, right? From the distribution station, it'll go in different directions across these. They've got them labeled as pylons here. You've probably seen them on the side of the interstate. For the kids here on the Avalon Peninsula, if you drive down the outer ring road and you look, you'll see these just off the side of the highway, and they just have the big wires hanging from them as it goes, to downtown St. John's or to each neighborhood. So the interesting thing is a lot of those power poles or pylons or what have you, because you transmit this electricity through the lines at such high voltage, and there's a reason for that. It's more efficient to do it at higher voltages than it is lower voltages. You have to then step down via a transformer, which there's a picture of in the top right-hand corner of the screen here, to something that the appliances in your home will use. Common voltages used in the home are in North America anyway, are 120 volts or 240 volts. So where the transmission lines will be between like 15,000 volts or 10,000 volts, you can't use that in your home. It would literally destroy the appliances trying to use it. The voltage is too high. You step that down with a transformer to 240 or 120, and then you deliver it to the wall sockets in your house, and you can plug appliances into them and use it.
Mhm.
The grid is regulated not only by federal and local governments, like country, province, state, for those in the US, but also the people that spent the money to install the transmission lines, the providers. In Houston, you have hundreds of them to choose from. Here in Newfoundland, it's Newfoundland Power for Labrador and Newfoundland, kind of the island we're on here. In fact, if you didn't know this already, I did not, in Hollyrod, there is a power generation plant that supplies the majority of the electricity for the Avalon Peninsula. And it's not 15 miles from you, 30 kilometers from us. Most of these transmission lines, by the way, are the copper conductors that the electricity flows through. So it's the same physics concept from generation of electricity, where the copper coil is spinning inside the magnets, to the lines that carry it across the country, from the power plant to the distribution centers to the substations, and then to your house. And then even inside the walls and attic of your house, the individual circuits or copper cables that connect to the power outlets where you plug in appliances. If you look at the plug that you're putting in the wall, there's metal prongs on it that are designed to let electricity flow in a certain way for the appliance to work like it's supposed to.
Mm.
So in North America, we have a multitude of grids, different ones. In the United States alone, there are 3. These are kind of, you can see on the page, they're subdivided across more North America, but in the US alone, you get some smaller localized grids. There's West, there's East, and then there's Texas. Of course, right? Texas has its own grid.
The
And it's
Western
managed by
region, the Eastern region, and then there's
Texas.
just Texas.
That's right. Newfoundland, as it turns out, is not dissimilar, right? What you can see on the map on the left are the main managing companies for those grids. You can see ERCOT or ERCOT for Texas. That's who manages the Texas power grid. And really, it's their responsibility to make sure that enough electricity is being generated to meet the demand for the homes and businesses that it's applying it to. That's what each of these 3 or 4 letter acronyms are supposed to do. They say, hey, somebody wants more electricity, we need to generate more. Because what did the video say about our ability to store electricity when it's not needed or demanded?
You have to make it.
You can't
Battery.
store very much electricity. You can't store it in very much quantities.
Okay, I heard you got to make batteries to store it if you need excess for emergencies. I heard you can't store very much of it. I would agree with both of those. Any other takes on it?
Only generate it when you actually need to use it. So
That's
like
right. That's very good. I didn't mean to cut you off. Do you want to finish? Say that, make that statement again. Repeat what you said.
Well, basically, you only generate the electricity when you need to use it, basically.
Exactly. There are hundreds of people, probably thousands, monitoring the electricity needs around the world, of every region in the world, just to figure out how much electricity they need to generate. Is it more? Is it less? Are there power outages? Because you can only use the electricity that's generated, but you have to generate enough to meet demand. If demand goes down, you can't just generate electricity because it's got nowhere to go and you can't store it. So they will literally
I'm not
shut
drawing this.
shut down plants and turn on plants as needed to make sure enough electricity is generated.
Interesting.
That's a very expensive thing to do when you think about operating a several megawatt plant that you just want to turn on or turn off. Some you can.
Sounds pretty easy, but I doubt it is.
Well, some like burning fossil fuels are easier. You just turn off the fuel, right? And then you get no more combustion, you get no more steam production, no more turbine, no more electrical generation.
Well, what
But
about like hydroelectric plants?
You have to stop the flow of water.
So do they just like close a wall underwater or something?
You can do that if the high side, remember we showed the graphic of the dam where the water on one side was higher than the other.
Mhm.
You risk doing that because if that water on the high side continues to raise because you're not letting any water through the dam, you could flood anything that's up there with it, including homes. So you may have to let a little bit of water through just to keep that water level down and flowing through the dam. The other thing you can do from a mechanical standpoint is disconnect the turbine shaft from the generator shaft. That way the water's still flowing, the turbine's still going, but the generator isn't turning. That's called an interlock or a mechanical linkage that you can break or disconnect. You're not really breaking it. You're just saying, no, I don't want to generate electricity right now, but I still want water to go through.
So is that like taking like, would a way to do that would be like, would it to be like taking two gears and make it so they don't connect, so one gear turns but the other one doesn't, things like that?
Exactly right. Your car can do the same thing. If you don't want it to go anywhere, you can put it in neutral. I'm thinking of a manual transmission where you can push in the clutch and literally disconnect the engine from the transmission. And when you let off the clutch plates come together and the RPM from the engine shaft and the torque generated goes into the transmission and makes the wheels turn. Same mechanism. You can do those things. I see that y'all are grasping this very well, and I had to go to engineering school to do it, so I'm happy for you. You can disconnect the two whenever you want power or when you don't, rather. And when you want power, you could put the two back together and generate. Man, y'all are ahead of the curve. I'm impressed.
So I have a Lego set, and basically you flick a switch, and depending on which way you flick the switch, different gears mesh or something, and like so depending, and then you can turn a crank and different things would happen. So that's like kind of one thing I think.
Kind of amazing, isn't it?
Yeah.
Fascinating. I started the same way. I had Legos too, except I didn't have switches and gears and stuff. I had to make them. But that's what inspired me to become an engineer. Seeing how things work like that in gears specifically, there's so much engineering and science that goes into the design of gears and gear systems. And there's so many different kinds that are better for one thing than another, depending on what you're doing. So that's awesome. So key takeaways, you might see this in Kahoot. You might see something like it in the Kahoot about the infrastructure. We know how a generator works. We know the different ways of making those generators turn and producing electricity. We know that large power plants do this to provide electricity for surrounding areas. I'll ask one more time, please don't draw on the screen. It's not time for that yet. Thank you. It goes through distribution centers first to get sent to more rural areas or to different cities. And then it goes through substations. It gets stepped up and stepped down along the way before it enters your home. So it's useful for the appliances in your home. Storing enough electricity to meet demand is difficult. It's very expensive. It deals with batteries, which have some other issues that come with them. So facilities have to be started and stopped based on demand. And there are companies that help manage the grid, service providers that we pay for our electricity to do so for us. They're the ones that actually turn the switches on, off. I need more demand. I need more electricity. I need less electricity.
We
And I thought this
are
picture,
all connected.
I thought this picture was a great summary. It's from NASA, and it's a composite video or a composite picture of the globe showing at night all of the electricity we use for lighting. I think we heard in one of the first videos that almost 80% of the electricity we use is for lighting. So we can see. You don't need that during the day much, unless you're indoors sometimes. But at night is when we use the most for lighting. Not the most electricity, but generally the most for lighting. Now,
A bunch in Australia.
very, very rarely is it dark across the entire globe at the same time. I can only think of one instance when that would be, and that's a solar eclipse, and it only lasts for a minute. But NASA put together this picture, and to me, it represents how connected we all are across the world by the electric infrastructure, by electricity. You can see certain parts that have more demand. Look at Europe and look at the United States. North America in general is extremely well lit at night. But
And
if
then
you look at
North
areas that
Korea and you see nothing there.
you see some,
I believe that how they took this picture is they went around the world taking a video, and as they went around, they kind of like followed the night. So like the whole way they went around, they always only saw night because it was going at a certain speed and direction.
they call that geosynchronous orbit, and you're correct. NASA has a photo satellite up there that's just taking images of the Earth. As they have multiple of them actually, but they built this picture based on that. You're right.
Most of the lights are in in the USA. Places are more lit up on the very edge or the side of North America.
Yeah. Kind of toward the East Coast. Yeah.
Yeah.
Where's
Japan is almost
Japan?
all lit up.
Japan is extremely well integrated. But
And you can
to me,
see that like pretty much most of the light on Newfoundland is just on the Avalon Peninsula, right at the end.
That's right.
Oh yeah.
Why do you think that is?
Because that's where the capital is, and that's where like most people live in Newfoundland.
You're exactly right. Almost half of the island's population lives on the Avalon Peninsula. Half of the province's population.
Half of Canada's population lives on the.
Not
Wait,
Canada.
I thought Canada had states.
I'm like, that's not a lot of
Provinces.
people in Canada.
Canada has provinces.
Yeah, I literally, so basically every place you studied so far, nobody else has states, which I find really strange.
This will blow your mind. There is only one state in the United States that still has parishes.
And so it's what?
Parishes
What are those?
instead of counties. You know,
Wow.
Texas has counties
Oh.
like Montgomery County where you live. There's one state in the United States that still has parishes.
Rhode Island.
Which
I'll
one?
leave you to think on that.
Which state?
We're all confused now.
Louisiana.
Google it.
Louisiana.
We live
We
right
passed
next to Paris.
My dad was
Oh.
born in Louisiana.
Me too.
Is it because Louisiana is kind of a French descendant?
Yes, that's correct. And a parish is a local division for churches.
Uh,
So it was set up as parishes, named mostly after leaders of the time, 1800s when Louisiana Purchase happened. 1803, actually. But anyway, back to electricity. That's the lesson, kids. Any questions?
Nope.
You have no questions.
No questions.
You guys really seem to be getting this. I'm seriously very impressed.
Concerned.
No,
concern.
I cannot overemphasize how important it is to understand these concepts because it is the challenge of the future. We are only going to increase our needs for energy across the globe as other countries develop and we continue to develop. It will be the issue that your generation is faced with figuring out. And you have to participate. You're either going to consume energy or you're going to consume energy and figure out how to make it more efficient.
You're gonna consume
So-
energy either way.
That's the only choices you got. You're going to participate in this system. And like the last picture showed, we're all in it. If you think we're different, we're not so different.
And people say in the future we're gonna have so much great stuff.
We are. If we try, you just have to put in the effort.
Do you want me to
So-
show some pictures or?
Sure.
you
If
here?
there's
Don't
no
share
other
it now. We're still
questions,
recording.
Okay.
It has our emails on it.
Yeah.
No, I
recording.
gathered,
Wow.
I just gathered some of the ones from the other day that you guys downloaded. I'm gonna just share, not from the.
I have a picture of mine.
Here, let's see.
let's see. I am eager to see these. I didn't get to review all of them before, but I did review the test questions and you know how everybody was doing on some of the written exercises.
It takes a second to load to them.
While that's pulling up, the next section is going to be on, well, now that we know what energy is and we've talked about how we generate electricity, the next section is going to be on using fossil fuels to do it. So we're going to talk about the good things and bad things about fossil fuels, the different types of fossil fuels there are, and get our foundation laid there.
Are we still using Switch for all the
Yes,
pre-work?
Yeah, there's just other stuff
we
that
give you
they
a score?
should. Hey, that's Levi's.
yes.
Yep,
And that's mine.
So
I
much
like
for
it.
anonymity. Let's see what we got. Very colorful. Generator transfer to the pylon or the transmission lines, stepped up to the distribution center, and then step back down to the homes.
Yeah,
That's
I
right.
forgot to label everything else.
Mine
I
was,
realized
I
that.
think, like one above Levi's.
Okay. That one's
Yep,
pretty.
generator, power lines. Yep, transport electricity to distribution centers. Yep, steps it down. Yep. Very good.
Yeah, that's mine.
Love it. I like it's red. You know, the
They
difficult thing
make
about
some-
electricity is you can't see it.
Yeah.
So if you see copper wires, you don't know what's got electricity in it and what doesn't.
Interesting.
So
Excuse me,
Don't
I'm
touch
just
copper.
curious. Where was this, was this a little project they were supposed to do? Because somehow I missed it. I saw their tests, the little quizzes, but was it in there with one of those quizzes?
It
This
wasn't in one of the
project?
quizzes. It was a separate assignment in the same module in
Because
the
the-
Switch classroom.
Yeah,
Yeah,
Okay, I get
so
it.
it's
It's
it
visual
says you watch the video
representation.
with,
And then that.
yeah.
It's always called a visual representation, so.
Okay, I
Yeah.
didn't see it. Okay, I'll take a better
Well,
look next time.
I will, that this is a new curriculum, so I appreciate that feedback. We're still figuring this out, just like
Could
Zoom
be
for the first
100%
time.
my
right?
fault. It might not be, it might just be that I didn't look hard enough. I just, when I hit assignments, I saw like multiple choice type things, but I somehow missed this one, but
That's
you
right.
showing-
When you, I'm gonna show, is everybody seeing my
Yep.
Yeah, we're seeing
my
it.
screen there and then? Okay, so here's the classes so far. If we go into, I think it was the power grid for that example. I have some other options here you may not have, but if you enter that lesson, and it decides to pull up, it's thinking.
It's thinking.
I thought this would be a good idea. Here we go. Okay, let ignore everybody's completions. This is not to out anybody. Thank you for everyone who took a look at it. Even if you didn't, I hope you enjoyed the lecture on it, because that's the conversation and reinforcing the concepts is the point, right? I would encourage you to do the lessons again.
you can go to Emma's. Emma's
Didn't do it.
Emma Energy.
And I was like, why?
Right. So these are the three activities you'll find under the assignment. There was a video to review, a couple minutes long. There was a quiz associated with it. And then below that should have been the visual representation assignment. And it gives you this question and asks you to make a drawing, including the following elements. And that's what was submitted. It, I think in the software, it'll allow you to upload that photo if you want. You don't have to, but that's where the drawings that Miss Tara just showed came from.
Okay.
Yeah. And if there's ever a visual representation again, usually the day of class, I'll go through and see the status and who turned them in, and then I can pull some of the ones that had drawings and stuff.
So again, those are just the, driving the concepts again is the point. Oftentimes when you write something down, you remember it better. So if you made a drawing of it, maybe it'll,
But
the structure of the grid will stick.
Who? Oh, now, do you want to play Kahoot, Mr. Michael?
I've got to go.
Oh, okay.
Duty calls.
Adios.
now,
I'll make time for one of them, I promise.
Not
I'm
that, I
really
mean,
just
Bye,
worried
Mr.
somebody's gonna
Mike.
beat me.
thanks for the class.
You're all very welcome, and we'll see you next time.
Thank you.
Bye. See you tonight, Dad.
Bye. See ya.
all right,
So are we gonna look on this? Yeah.
Now for the Kahoot.
time for the Kahoot. So
I
again, you just go to kahoot.it and put in our game pin.
We'll have to stop whenever it's time for story of the world. Just so you know.
this one.
Okay, let's go ahead and.
Ignore that.
What how do we do it again? I don't know.
So you
either.
go to www.kahoot.it, and then it asks for a
Yeah,
game pin.
You can type Kahoot and it should pop up.
Game pin 4873986. Is it working? Because I don't see players. Did I do it wrong? Okay, there we go.
I'm redoing it. Maybe put the.
Okay.
We're loading.
Okay. I thought it was on my end again. It always lags.
No.
Okay. No.
All right.
Pizza.
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 What?
Pizza.
What's that?
No, it looks like a. Please, can we do the hamburger? Hmm? But there's a propeller.
It's unusually quiet.
I know. And we got 7 in Kahoot. I wonder if, let's see how many people left. Because I know we're kind of over
There's
time.
10 people in this, including you.
Oh, I stay
Mom.
quiet until it's like the midst of the Kahoot, and then
Yeah.
I'm like screaming.
So I expect there'll be probably one person more doing it. so.
Okay. Let me know if you need extra time. If not, we can start playing.
Once my sister gets back.
I'm back.
All right, yeah, that should be all because the other people in the Zoom is just you and my mom. So
Who's battery?
Oh,
Thank
I'm
you,
battery.
Lola.
battery.
All right, y'all ready to go? Speak now or forever hold your peace.
My piece is not held.
Okay,
Yeah, I'm ready.
then let's play.
No.
At home.
At
Or
home.
homeschool, that's perfect.
Electricity. Do anything about
Oh, wow.
This is time to redeem yourself.
To redeem yourself.
Redeem. I need redeeming.
Wait.
Did you make this Christmas star?
I am 6th place. I
That
got
music
it
is
wrong.
kind of like
I'm
breaking
gonna
up.
be like 7th place now.
What's the question? What is the course that holds what?
Oh, never mind.
The music was
Now
breaking
we're
up.
all the way in the I didn't even see the question. That one. No, this one.
I heard that one. This one.
No, probably. What does innervate mean?
I don't know.
I don't know. I just remember answering this question correctly. I think it's like calculate, or it must mean calculate.
Yeah.
That's what happens when the words change on you.
Yeah.
99% of the world's electricity is produced by generators.
Win.
Wow, you got that
You
one
said
fast.
the answer.
Grace, are you running wild?
Great. Is it real?
Victor's so innocent.
Mm. Innocent, huh?
That's bull.
Does Victor listen to our lessons?
Yeah, no.
Wait for it.
4%?
Every now and then I just hear bum,
Wait for it.
bum.
Hey.
I'm in 7th place.
Good job.
Aim for the podium next time.
Just like you're
Yeah.
Right?
It says that like we don't aim for the podium.
Oh my.
Hello. Let's see, but oh right. Is it red?
I just want to get
Is
one
it
right.
red? Mine red.
Victor be yelling out the answers.
It's red.
I wouldn't trust him, so.
Battery.
That was luck.
It is a
Time
time
measurement
measurement
for kids
for
playing video
kids
games.
playing video
I want to
games.
know who Running Wind is.
Running wind.
Yes.
Oh, running wind
Yellow.
or running wild. I thought it was running wild. Oh,
yellow.
that's Grace.
Yes,
Obviously.
yellow.
I think. It's like,
I
I
accidentally
said running.
texted you to say.
Only
say it
because I said
right.
running. Yeah, I can't really respond to your text. in
Uh,
It is all an illusion.
Is it all an illusion?
Green.
It is all an illusion.
What? Mine green.
Reality
Emma, who are you?
isn't true. I'm Rutro Raggy.
50-50 electron.
Yo, Matrix, reality
No one
is
said
all
it would be
illusion.
easy wink emoji. It gives me a wink emoji. They think it would make that
I
better.
hate Kahoot. I'm slowly having a grudge on it.
Kid,
just
it's
have
kid
this
energy. Kid energy.
Hamsters on
Wheels
wheels.
on wheels.
It's red again.
East West
and
yeehaw.
Yeehaw.
East West barbecue.
East West
and cowboy.
barbecue.
Cowboy.
Honestly, I think
I'm
all
a
of these are
cowboy.
correct.
I'm going.
East West. Grace, you remember our Yepperdoodles
Oh, it's
thing?
green.
Mhm.
Yeah.
Green. I gotta get. Let me get the color.
One game of
I
Fortnite. Wow.
get.
Every hour, enough energy from the sun hits the Earth's surface to power the world for one
Hi,
game of
guys.
Fortnite.
Foolish shy guys.
For one game of Fortnite.
First place. Come on. Let's see if I can get the right one. It's it.
Photovoltaic sounds scary. Photons aren't real.
Because it's yellow. It's red. It's
Foolish shy guys.
blue.
Cave monsters thrive in the sun.
Red. Yellow, green.
It's not right.
Darkness,
Monsters thrive in the sun.
technically, yellow isn't wrong.
It's green. I think it's green.
But it doesn't answer the
Yeah,
question.
I think you're right, Victor.
Generators work. They do work.
By using robots.
Using
Kids after eating
Using
sugar.
kinetic energy of
Or eating
kids after eating sugar.
No.
Yo, that would be the next. That's gonna be the next energy. We're going to harness the power of energetic kids.
They will hire kids to eat candy.
Oh,
it's
that
the
sounds
perfect job.
yummy.
Grace
I
is
can make
like,
my
"Yay,
child
can't
work.
wait."
It comes from aliens.
Gives me superhuman
No, no,
abilities.
it is a
It's
secret to a health diet. The ultimate secret.
A transformer is.
Wow.
I mean, they ain't wrong. The first two ain't wrong.
I mean,
That's yellow.
They're actually all
Bumblebee.
kind of right.
A transformer is
That
Bumblebee.
is true.
Yellow.
Lightning bolts.
I think I got it wrong. Typically, small household appliances in North America uses
Oh.
1 voltage.
Probably got it right. What?
Yeah.
I know. Large.
I know.
Large volts.
This one I also think I got wrong.
Yeah, I'm pretty sure I
probably
got this
did
one.
too.
Oh,
Oh, yay, I got it.
oh.
Woohoo!
I ain't gonna say blue.
Yay, I'm at least seeable now. Sitting in a pool of Jello.
Shocking your mom. by
Stalking your
cleaning
mom by
room.
cleaning your room.
I'll definitely shock my mom.
Typically isn't shocked when I clean my room.
I would probably shock my dad more though.
No.
So
I'm
who
in
chose
sixth
green?
place.
Who chose
Finally.
green?
Challenge questions.
But I
Ohm's
took
law says.
law
Oh,
says.
oh.
But I
Voltage equals MC squared.
is it blue?
Ohm's law. Ohm. Y'all know that one kid from Odd Squad that was named Ohm?
I haven't
No,
watched Odd Squad.
None of
in
you watched
years.
Odd Squad?
I watched Odd Squad, but I don't remember anything.
How did you get your education?
Mario M. Luigi.
Mario and Luigi.
Bacon times eggs. What is this?
Nah, egg times cheese.
Same. I say scrambled eggs and cheese. Here, boys. Wow, this is lovely.
Art class. How I hate art class.
Oh well, this is just lovely, fellow friends. Oh, I got it right team. That's a big surprise.
Electricity is a figment of our imagination.
Electricity isn't dangerous.
It's just a figment of our imagination.
Common.
How do we get to the other?
Burning,
Eating
eating beans to create wind.
Eating beans can create when Again, you could hire the kids.
Hide. Electricity is commonly said to have discovered.
Oh, 600 BC.
Yeah.
Aliens brought it from another
Aliens
time.
brought it
Yeah.
from another
They said
time.
so.
Aliens brought it from another time.
They said so. Mama, come see. Come see. Answer correct. Answer correct. 7.
Oh man.
5.
Oh man.
I think I was.
It
number
told me
4,
the
though.
same thing you did last
That's
time. You have the
perfect.
podium next time.
Man. 16.
Well, that didn't. Luckily for me, it didn't.
And look
say
at us,
anything.
Chad. And we were on the last
The
Wow.
stuff legends are made of. Wow.
place.
Yeah.
Hey, it's only
Crazy.
fitting that the
Podium.
winner of the electricity thing should be a battery.
Who was battery?
Oh, that was me again.
Levi.
Okay, who was on the podium?
Who
Got
is so
second place.
encouraging? Whenever
I was on
you
the
get an answer
podium.
wrong.
Nice.
Yeah, Grace
Great
was.
try.
I was right behind you, Grace, but not really right behind you because I was like 2,000 points behind you, but still.
Good job, guys.
I was rut-row raggy.
Rower, of course.
Go figure.
All right.
I
who
was
Get
wants
an
the
answer
question
wrong,
from the-
please.
Emma. Did it say aim for the podium next time?
Yeah.
frog.
So it's so encouraging, right?
They say
Mhm.
it like we do.
Yeah,
So
like you're not
podium.
aiming for the podium.
Definitely not temper inducing.
I know.
Well, that was a good job, guys. Here, I'm gonna set